to achieve, large differential mode voltage gain. Okay, so in a differential mode voltage gain is we may have some negative sign. Driver transconductance GM2, GM3 plus all those arrow things. Yeah. So if I increase VDD prime, then my GM3 will increase, right? GM3 will increase. So, yeah, sometimes, yeah, if I increase VD3 properly, this transconductance can be 0. The load resistance can be infinite, right? Yeah, we can adjust that by using LC oscillator. Our LC is something like that. We need a gyrator, right? If we have a gyrator thing is here, say I have a GM thing here, and then I have a capacitor there, okay. Then this looks like a inductor, right? This is inductor GM square over C, C over GM square, I'm not sure. Which is which? L over C. Yeah. C over GM square. Is it right? Yeah. I think this is good. Square root L over C is a impedance. It should be 1 over GM. So, yeah. See, I want have an LC oscillator, something like that. Okay. Then, see, I can put C there, right? If I put C here, then I have a LC, this LC resonant circuit, okay? If you put capacitor there, then it doesn't actually, yeah, we should put capacitor there, then we have a LC parallel circuit. So we want to emulate this, actually what's this gyrator looks like? Gyrator is nothing but I have a GM thing here, and then see this is plus minus plus minus something like that, right? Say I have a capacitor here, and then I have another GM here. Let's just see. Yeah, it should be connected. So I'm looking. I'm actually let's draw a single-ended version. Say this is a plus plus. Is this plus plus? Yeah. And then I have a C there, and then I have another one, plus minus or something like that. Right? Yeah, this is my gyrator, right? GM. I have a non-inverting transconductor and the inverting transconductor. What's the differential version? The differential version of this gyrator can be, yeah, I have a differential version. Then I have a capacitor here, and then I need let's just see. Is this the one? Let me see. Let me check the circuit. Okay. Let me redraw this thing. Plus minus minus plus, okay. And then so this is my input, and then here I'm crossing this thing to generate Actually, this is a non-inverting version. Plus, minus, minus, plus. Okay. And then this thing is connected to there. Say, if I put capacitor here, yeah, this is my LC resonator. So we'll see inductor here, okay? And then we have a parallel capacitor. Yeah, so for this, actually this is my nota cell, okay? So I will adjust VDD prime for the GM3 to sustain oscillation. So if my output resistance, GM2, GM3, and then all those resistance, if this resistance, this conductance becomes 0, then the output will have some oscillation, right? It has some, frequency is dependent on GM over C. Just frequency is actually square root LC. Oscillation frequency is like that. Okay, this inductor is only GM, C over GM square, right? Times, let's just see. This is a C, right? Oh, yeah. Okay, so my oscillation frequency will be GM over C, right? Okay. If this thing becomes positive, then oscillation will die out, right? Die out. If this thing is negative, oscillation will grow with the time, right? And then it will saturate somewhere, and then it will saturate some at the supply voltage. So when for the proper VDD prime value, this becomes 0 and will have some constant amplitude oscillation, right? That's a Q tuning. We can adjust this GM by using some Baselock loop to set oscillation frequency to a fixed frequency. Okay? So we have two kinds of tuning circuit. Question? No question? Okay, let's repeat a little bit about this VCM generator for another. This is another version of inverter-based amplifier. So for this inverter-based amplifier, this is not nota cell. So, in a nota cell, common mode is controlled by a cross-coupled inverter, right? This cross-coupled inverter. Yeah, this one controls to fix some common mode, right? Yeah, but in the second version, we want to use, let's just say, yeah, we want to use those two inverters in parallel, but we want to control common mode by some different means. See, for example, yeah, this is BIP, BOM, BOP, BIM. Say, we take just a common mode output, use a differential amplifier, and then put some, this thing is some connected to some logic threshold or something like that, okay? This is a logic threshold, okay? And then we can use inverters like that, okay? to control common mode. So then this should be negative, positive, right? So this part is a CMFB circuit, right? This is in the nota cell. This is a kind of CMFB, right? A kind of CMFB. Actually, there is another thing. This bias. This is still complex, right? So in the nota cell, common mode gain is pretty large. It can be larger than 1. Okay, that's no good. But in this game, my common mode voltage gain can be pretty small. Then let's just see, what is my differential mode gain? For the differential mode gain, yeah, this is for DC, so it doesn't drive. Differential mode gain can be just GMD times that arrow thing. This can be RO2, GM2 RO2. I don't know whether you can apply this one here. Say you can apply this one here to increase common mode gain or with a CMFB. Okay, I didn't try yet. So this is the second approach. So for this second approach, there are two kinds. See, I can adjust this VDD to set. By using resistor. Okay. So for this second version of this pseudo differential op-amp, so the first approach is this. Say I will use. So this is my inverter. So this is a replica circuit. So where is my inverter cell? Oh yeah, this is my inverter. Okay. So I have two inverters here, and then I have some common mode output voltage here, some shunt MOS transistor, and this resistor. So this voltage will be this voltage is supply voltage of this inverter, and then it will be adjusted to set this inverter to certain GM value, right? For the inverter, the current through inverter is if my VDD is 3.3, and then this will be my current, right? So my GM at the logic threshold will be determined by this current level. If I reduce my supply voltage to, for example, 3 volt, not 3 volt, 2.5 volt, okay? Then my current will be something like that, okay? So then this is my logic threshold. The current will be much lower. I have a much smaller GM, right? So I want to set my GM by this circuit. Yeah, I want to determine this current level. This current level is the current level at the logic threshold of inverter. Yeah? So then if I flow this IREP current and then 2x1 MOS transistors, then this current should be same as IREP. This current should be always also IREP, right? Because this current is 0. Then I have a differential amplifier, So connecting this one to minus input node, this voltage to VM connected to plus input volt, and then generate some VCM voltage apply here, right? Then I have a negative feedback through this branch. Okay, negative feedback. Yeah, this negative feedback will set virtual ground for between those two nodes. So my VB will be same as VM. Yeah, this is nothing but logic threshold voltage of this inverter, right? Because input and output are equal to each other. Okay. So then this inverter works at the logic threshold voltage, logic threshold point with some VDD prime here. This is a VDD2 maybe. Yeah, some current flow through this resistor. Oh, I think this is 5,000, 5K. It adjusts the VCM voltage and adjusts this bypass current. It flows through 5K resistor, and then it will reduce supply voltage of this inverter. So this inverter works at the logic threshold with a current of IREF, right? Then this IREF determines the GM of this inverter. If I broadcast the VCM to all inverters, then all inverters work at this current at the logic threshold. Okay? Question? No? Okay. No question. So let's just see. I think we did it already, right? Did we? We simulated this part, no? Let's review then. VCM. Yeah, it's exactly the same circuit. So here, see, we'll sweep this current level from 0 to 60 microamp, and then find all those supply voltage, right? Supply voltage, yeah,